Lari-dari. Okay. Okay, so last time we talked about one main thing, but introduced the second. The first was we talked about nuclear shielding and things like effective nuclear charge and radius. And you can predict a lot about a molecule's properties if you understand those concepts. 2 points there. As you go to higher principal quantum numbers, the electrons get further from the nucleus. That means the atoms get bigger. That means they shield less well. It also means they're not as tightly bound. So generally, when you go down, the electrons get easier to remove. That makes iodine more willing to give up its electron than fluorine. Cesium is really great to throw into a puddle of water. Lithium's a little boring by comparison. The other is that F orbitals don't shield the nucleus very well. They don't extend away from the atom very well. They're kind of boring, right? Because they don't shield very well, you add protons to the nucleus and electrons to F orbitals as you go to the right across the F orbital block, and the effective charge goes up because those electrons don't compensate the charge very well. They don't shield the nuclear charge well. And then after that, you start filling the 5Ds, and all of a sudden, the atoms feel very electronegative by comparison. That makes them shrink. That makes them more electron withdrawn. Okay. So another principle I noticed that I didn't mention actually is something called relativistic effects. Relativistic effects occur when you have very heavy elements, basically those after the F orbital block. The electrons around the nucleus are thought to orbit so rapidly that they undergo relativistic contraction. This makes the atom shrink. Okay, that's something that also contributes to the small size of the 5D transition metals and to things like gold. Supposedly, it explains why gold's color is gold and not silver. I don't know why that's the case, but that's what everybody says. So I promised to type all those principles up to you since I just read them from my notes, and I haven't done that. So I need to do that. And then you will have a handout available online. Probably not today, hopefully tomorrow. The other thing we introduced was something called natural resonance theory. Natural resonance theory we're going to do more of today, so I'm not going to spend a lot of time talking about it, but it's a way to draw molecules that avoids breaking the octet rule, which is something I want you to practice. And so we've made the problem set instructions kind of restrictive to force you to use this approach. Okay, so on the problem set, don't draw structures that violate the octet rule or you're going to be marked wrong. People are going to do that and they're going to be annoyed, but those are the rules of the problem set to force you to try and adopt this other way of representing things. Okay, I'm going to break the octet rule to show you examples and make things clear today. Don't do that on the problem set. Okay. All right. So probably you're used to drawing Lewis structures. I've written up some instructions on how to do it if you're not that familiar. Basically, start by drawing singly bonded structures. Look at the atoms and ask, particularly the central atom, whether or not it has an octet on that basis. You can add pi bonds to raise the valence of the atoms if you need to, and then add lone pairs and add formal charges after that. So we'll do some examples of that kind of thing today, starting with sulfate. It's a 2-. So I'm going to take a sulfur and surround it with 4 oxygens. We have indicated the central atom on the problem set in almost every case. I think OPN is not referenced. The P is generally the most electropositive element, will go in the middle. Sulfur is more electropositive, oxygen is more electronegative, so sulfur goes in the middle. You could draw an isomer, but that's not the structure of sulfate. You probably know what we're talking about. So here's sulfate, 4 bonds around sulfur. Each normal covalent bond has 2 electrons. Sulfur has an octet of electrons here. Okay. Let's draw in some formal charges, or sorry, some lone pairs. And before I continue, you might ask, well, how did you know to draw 3 electron pairs around this oxygen atom? That's because I know the structure of water. Pretty easy. I know the structure of ammonia, hydrogen sulfide. Those just have hydrogens to fill the valence shell. And when there's a hydrogen missing, there's a lone pair left behind, generally. So you can think about oxygen having 2 bonds to water and 2 lone pairs. You know that reference structure. Here we've got 1 bond, so we've got a hydrogen missing, so to speak. That leaves us with 3 lone pairs. So that's how I do that mentally. The lone pairs raise these oxygens up to an octet. They have a normal covalent bond, so that all looks hunky-dory. So what's missing from this drawing? Formal charges are missing. This thing is 2 minus overall. The formal charges that you're going to see here should add up in total to a 2 minus charge. Okay, so if this is like hydroxide, this thing here, I know that's a negatively charged thing. I see 4 negative charges, and I can put a 2 plus here to get to 2 minus overall. Okay, that's how I do the math. There's another way to go about it, which is to take this structure and to break these normal covalent bonds in half. How many electrons does sulfur have around it if I homolize or homolytically cleave those bonds and send 1 electron to each atom? That leaves 4 electrons in sulfur. How many electrons does sulfur have in its neutral state as an atom? 6. So I only have 4 electrons on sulfur, and there should be 6 in the neutral state. That means 2 have been lost. Okay, so 2 different ways to do that. You could do the same thing for oxygen. If I cleave this bond in half and I send 1 electron over here, this oxygen has 7. The neutral atom has 6, so it gets a negative charge. Okay, that's the other way to do it. But I'm used to thinking about simple organic compounds, small molecules like water, hydroxide. I know if there's 1 bond to oxygen, probably it's going to have another electron and a negative charge on it. Okay. All right. So this obeys the octet rule. Nobody draws sulfate this way except Jed Parker. Okay. But this obeys the octet rule, and this is the right answer. All right. Let's draw some structures that don't obey the octet rule that look more familiar. All right, so one of them is where you take a lone pair and you push it down onto the sulfur and you make a double bond. Now, by pushing that electron pair down here, now if we cleave this bond in half, we send 2 electrons up to that oxygen. There are 2 lone pairs left behind. That oxygen has 6 electrons when you homolize that bond. So that's the same as the neutral atom, no more formal charge. Now, you've gotten rid of the negative charge here, you better get rid of a positive charge down here. You got to produce a compound that still has a 2 minus charge overall. So now this is going to be just plus. And there are 4 of these. And none of them obey the octet rule. Why don't they obey the octet rule? The sulfur has 5 bonds, right? That's 10 electrons. You can't have 10 electrons in normal covalent bonds. That doesn't work. That violates the octet rule. We don't draw structures like that on our homework set. This one's pretty common. We'll see this often. Right? We just did it again. Took a lone pair, pushed it onto sulfur, neutralized some charge. It's pleasing because it doesn't have a bunch of charges all over it. This thing looks gnarly. You've got all these positive and negative charges everywhere, right? So people like this because it's neater, but it's not a good description of its electronic structure. How about this one? What's the matter with that? All kinds of things are wrong with that one. Of course, it exceeds the octet rule, but what's the other thing that's really wrong here?
Oxygen is a more atom, so it shouldn't be maintaining that positive charge.
Yeah, I mean, when you think about the atoms involved here, you have to ask, is this a reasonable charge distribution? It's not a reasonable charge distribution because oxygen is much more electronegative than sulfur is. Okay. All right. So generally, don't draw the positive charge on the more electronegative atoms. Okay. Now you might say, well, you know, Professor Owen, I mean, this sulfur's got all these electronegative atoms around it. So it's probably feeling kind of depleted. So I bet it's fighting back a little more than a regular sulfur might. Right? I think that's a good argument. So this has a little bit of merit. Right? It's just a very, very tiny amount. But there's a little bit of merit to that perspective. And I think if you looked at oxygens that carry, you know, in a variety of different structures, you'd find that that one is experiencing more electron withdrawing power than a lot of other situations for oxygen. Okay? So these resonance structures are sort of like pure forms of the electronic structure possibilities. The true structure is a combination of these sorts of things. I can tell you it's like 99.9% this one. That's what electronic structure calculations say. But you're not really wrong to say that it's kind of a little bit like those over there. It's just not that relevant. Okay, so don't draw that stuff. On the problem set, you'd be marked wrong for drawing those things. In real life, if you drew this, somebody would say, who taught you this stuff? You know, okay. All right, let's do this again. We're going to do another one. IF4 plus. All right, so we've got an iodine with 4 fluorines around it. This IF4 plus, you can represent this way. And it has 2, 4, 6, 8 10 electrons in covalent bonds and that lone pair surrounding it. So this structure violates the octet rule. Go ahead.
Professor, natural resonance theory, does it describe that all those structures are in resonance or just the ones that don't break the octet?
I would say that any depiction of a molecule is going to be like a limiting depiction, and a true description is some combination of those things. Natural resonance theory combines electrostatic interactions and covalent bonds as a way to represent the limiting structures. So I'm not sure if that answers your question very well or not. But when you want to draw something, you know, the molecule, again, doesn't care how you draw it, right? It has its own electronic structure. We're trying to represent the best. This is a way to represent it. So we'll do natural resonance descriptions over here that include electrostatic interactions to help make that clear. Okay. So this guy violates the octet rule because we have 2, 4, 6, 8, 10 electrons around that iodine. Okay. So this is hypervalent representation. There is one of the natural resonance depictions of this type of situation. There are 4 of these. Ignoring geometry. Okay, when we do these kinds of things and I ask you how many of these there are, typically we ignore geometry. You could, in principle, say, I don't really like that plus charge in the iodine out there. That poor iodine is screaming for electrons because of how electron withdrawing everything is. I'm going to draw this. And you know what? There are 4 of these, so it's okay. Sorry, I forgot my own character. So what did I do? Well, I took this structure here. I took an electron pair and I pushed it onto iodine. That's how I got a double bond. And if you cleave this homolytically, that fluorine's got 6 electrons. So it's better to have a positive charge. So you just took the positive charge that was on iodine and you pushed it out onto the fluorine by borrowing an electron from it. And of course, this thing breaks the octet rule badly. It's very hypervalent. But you've also put the more put the positive charge on the more electronegative atom. That's generally a no-no. Yeah.
So that's a lone pair on the right, it wouldn't make sense to, like, it wouldn't make sense to have an ionic bond with just the lone pair, right?
That's right.
Okay.
It wouldn't make sense to draw the electron pair separate from the atom. Yeah, good idea though. I should say out of the box thinking. That's the first time anybody's ever asked this question. Yeah.
So with that last structure, this breaks the octet rule, but
Correct.
in theory, you could take 2 of the singly bonded fluorines and push those bonds onto the fluorines for 2 of them.
Correct.
Which would restore the octet rule.
Correct.
And so that seems kind of outlandish, but is that considered valid, like say in the context of the P set?
Yeah. So let's draw that structure. Did I do that right? No. There we go. So there's a resonance structure that obeys the octet rule. How do you feel about that? Why is it ugly?
You've generated 4 charges. And double bonds.
Yeah, you've got a plus charge on a fluorine and a negative charge on a fluorine in the same molecule.
But in theory, this is.
It obeys the octet rule. Yeah, it uses the appropriate number of covalent bonds and lone pairs to satisfy our knowledge that only p orbitals and s orbitals are involved in making bonds.
If you were asked to draw all the structures of IF4 plus, would you have drawn this as one thing?
I would say that that is not a good structure because of charge separation. And this is an issue, actually. So you will draw structures like this sometimes and ask, well, you know, is this reasonable? And what you pointed out was, Al, you know, there's a lot of charges here. And a way to think about this is, you know, a plus charge on a fluorine and a negative charge on another fluorine in the same molecule, when the fluorines are indistinguishable, ignoring geometry, that's not a good situation, right? That's a high energy type of an arrangement when you have charge separation like that. That would be a way to think about it. So you want to be careful not to just draw charges willy-nilly and really minimize charge to the extent that you can. That makes sense, yeah.
I'm just gonna say theoretically, they're like almost infinite. I wouldn't say infinite, but there are so many structures that don't violate the octet, but I don't know if that just makes it. You could also do a triple bond and remove the third covalent. And there are
Correct.
all these crazy structures.
Yeah.
Just because everything has 8 electrons.
Right. Yeah, yeah. So, you know, I have noticed that sometimes people get really worked up about English grammar. You know, they come after you for, I don't know, for not spelling things correctly or capitalizing, using punctuation. And it's sort of a perspective that, like, you want to do that to the extent that is reasonable to get your point across. But if you're communicating well, it's okay to sort of ignore the rules of grammar, right? There's like a balance to be struck. You can imagine structures like this and say, wow, no, it's an interesting thing to consider, but it's not really a good tool for communicating what kind of a molecule we're working with here. So pick a structure that illustrates the molecule's properties as best as you possibly can. Sometimes there are multiple possibilities where you get combinations that are reasonable to consider and are worth talking about. Some structures are not worth talking about because they're sort of a fantasy, not helpful in describing the molecule, okay? That's good.
If we did have that, would there be 3 of them?
Yes, for 4. 4? Because you put the double bond on one of 4 fluorines, yeah.
So in the problem set, would you want us to draw the one that best describes the molecule?
Yeah, I really only want you to draw structures that capture the molecule. And you shouldn't leave out things that are reasonable representations either.
There's an example similar to the sulfate on the homework, so I wanted to ask. We know sulfate experimentally has a bond order of 1/1/2. So would it be reasonable to indicate that with that double bonded structure, one of the covalent bonds becomes an electrostatic interaction, and we get a separation with a 2+ and a 2- oxygen?
It is a reasonable structure to draw a 2- and on an oxygen and a 1+ on the sulfur. Did I do that right? I guess that would be a 2+ on the sulfur. It's not outlandish to draw something like that. You know, the bond length is a little bit tricky, I think, in that molecule. So I don't know where this idea that it has a bond order of 1.5 comes from.
Well, that's when we look at the, if we were looking at old hypervalent structures and we're looking at the combined resonance, we can, mostly all the oxygens have can either be double or single, and that would indicate 1.5.
Right. I think what you'd find is that the bond lengths are closer to a single bond. Yeah, I don't know actually, but that's what I would guess. That depiction is not a good depiction, so I wouldn't rely on it when guessing bond orders. TJ?
Are we allowed to make them polar covalent and use partial formal charges?
So for the sake of drawing Lewis structures, mostly I want you to just worry about formal charges. Partial charges will come from mixtures of Lewis structures that are fair representations. So as I was saying before, you know, you might say, hey, you know, this is not so crazy, or this is not so crazy, because I know this iodine really needs electrons. It's surrounded by 4 fluorines. It's a positively charged thing. There's probably some fighting back going on here, right? And so you might say, well, does it really have a negative charge like this? You know, or is it maybe a little bit of this? There are mixtures of these things going on. And we're not going to worry about deciding with a number what that mixture is, but just which ones are reasonable and make a meaningful contribution to the actual representation. You understand what I'm saying? But the partial charges are going to come from mixing the limiting charges.
So in this case, would the second and the fourth one be the ones that would be acceptable on the homework, or just the second one?
So I like this one the best because I see 4 electrons around iodine. And that makes me happy that this thing is obeying the octet rule. Okay. That's sort of the number 1 rule in the homework set, is that. And then otherwise, it has the best distribution of charge, I think. You know, this is probably my second favorite, but I think this is the best one by far. Okay. All right. Now, sometimes you're going to run into hypovalent molecules. What's a hypovalent molecule that has an atom with less than 8 electrons in it?
Boron.
There you go, boron. Boranes often are hypovalent. Okay. Another good one is carbon monoxide. Carbon monoxide is kind of cool. Oxygen gets to make 2 bonds. Here, it has an octet. Carbon does not have an octet. It has 6 electrons. Carbon monoxide is hypovalent. Now, you probably haven't seen carbon monoxide drawn this way before. What's another representation of carbon monoxide? How do we draw carbon monoxide?
With a triple bond?
Triple bond, and where does that come from?
That maintains an octet on each one.
Okay, so what else should I do to allow this thing to have a triple bond?
Or one of the lone pairs off the oxygen. Concentrate that electron density between the 2.
Very good. We'll take this guy and share them with carbon. This maximizes the bonding. Now, what happens when you push an electron pair over to share it with another atom? You're going to get a formal charge. Okay. If you want to covalently or homolytically cleave this bond, then you end up with 5 electrons around oxygen. That's +1. You better get a neutral molecule if you started with a neutral thing. Pushing the electrons around shouldn't change whether or not it's neutral, okay? Unless you ionize it. All right, so turns out this is the best structure. The major contributing resonance structure. Does that bother you? Why, Emma?
Because the negative is on the less electron.
Yeah, you wrote a plus charge on oxygen, negative charge on carbon. It's the inverse of their electronegativities. There's nothing you can do about that situation in a hypovalent system. Okay. You're going to find difficult judgment calls sometimes with hypovalent compounds as a result. So remember that each resonance structure we draw contributes to an extent. All right. Now, another interesting thing about carbon monoxide is that it has no dipole moment, essentially no dipole moment. Okay, so if I look at this thing and I ask, well, is there a dipole moment? The charge distribution says so. You know, oxygen, however, is more electronegative than carbon. Right, so is this the best description? What about this one? Probably kind of a combination of those two. That's how resonance structures work, right? When we draw a resonance structure, we're saying one of the pure forms. What's a pure form? It's like, you know, am I good at football? Well, I can throw the ball, but it doesn't make a spiral when I throw it. You know, so yeah, I'm good at football. I could be better, right? Which one of these is the right structure? It's a combination of them. This is my preferred structure because of the bond length that you see there. It also happens to be the case that there's no dipole moment. So this is maybe a little bit misleading, yeah.
What would be the hybridization on the oxygen? On the molecule, would it be sp2 or more sp?
Somewhere in between.
More sp, sorry.
It would be somewhere in between. So you're used to sp, sp2, sp3. This is a statement about how the orbitals mix. That depends upon the compound. Lots of things are sp 2.87. All right. Okay. Oh, yes. So this donation of an electron pair to this empty orbital on carbon is an example of a dative bond. Okay. The dative bond is where one of the partners brings both electrons to make the connection. I see your hand up. Just one moment.
So if we were to try to reconcile why that structure of carbon monoxide has no dipole, is it possible to say that although there are formal charges, the triple bond is like weighted more towards the oxygen, which kind of proves that?
Yeah. Yeah, you would say that the molecule is sort of polarized in a manner that solves this charge distribution and electronegativity problem. Yeah, and the orbitals of this thing bear that out. So, you know, if you look at the lowest lying empty orbital in carbon monoxide, it's concentrated over here.
Okay.
And the bond pairs are the pi bonds are concentrated toward the oxygen, the filled electrons are. All right, so a dative bond is a bond where one of the partners brings both electrons. You find them in hycovalent compounds. So let's do is chlorine. Okay, BF3. Boron has 3 electrons. 3 fluorines have 7 electrons each. That's 24 electrons total. Okay. 2, 4, 6. 6, 6, and 6 is 24. Now, if I cleave these single bonds homolytically, everybody's got the same number of electrons as they do in the neutral atom. No formal charges required. But this structure is hypovalent because this boron has 6 electrons in the bonds around it. It doesn't have a lone pair. Okay, so that boron is hypovalent. So let's maximize the bonding. When I push that electron pair from the fluorine onto the boron, I'm going to develop positive and negative charges, right? Because if I cleave this bond in half now, 6 electrons on fluorine is 1 fewer than the neutral atom. So it's got to have a positive charge. When you push an electron pair onto the boron, you get this charge arrangement. Same thing happened over here. Important to remember that. You're going to do a lot of it. So, is this a good resonance structure? How many people think it's a good resonance structure? How many people think it's a bad resonance structure? Okay. I think it's a good resonance structure. I know it's a good resonance structure, actually. These bonds are shorter than they would be normally. There's a lot of evidence for pi bonding between fluorine and boron in this compound. Okay. Having less than an octet is a bad scene. That makes these molecules really good Lewis acids. They're powerful Lewis acids. If you spill some on yourself, it will burn you. Okay, yeah.
So if we consider alternatively like BH3, hydrogen doesn't have any extra electrons.
There you go.
Let's solve that.
By obtaining electrons from somewhere else. But that's exactly right. There's no lone pair there. It turns out that if you go to chlorine and bromine and iodine here instead of fluorine, the bonds get longer. Pi bonds don't really work very well at long distances. And those molecules actually become increasingly acidic as you go toward iodine. That violates what you know about electron affinity and, about ionization energy. Iodide is more basic than fluoride, or more electron releasing, I guess I should say. More electron releasing, more electropositive. It's easier to rip an electron off of an iodide. But the pi bond stinks when you have an iodine because it's so far away. And that makes that boron actually a stronger acid. Boron triiodide is potent. Boron trifluoride is a pretty powerful acid too. But the pi bond here neutralizes it a little bit. Okay, so this is actually a decent resonance structure, despite the fact that you have that positive charge on fluorine. Now remember, there are 3 of these. That helps, right? So the actual amount of positive charge on the fluorine is reduced because of that. Okay, so you're stuck with this kind of situation when you have hypovalent compounds. It's not a good scene to only have 6 electrons. Okay? Things that have fewer than a valence shell are unhappy. All right, so. Back to Ethan's question. Beta bonding becomes very important for hypovalent compounds. A lot of transition metals are like that. When we do transition metals, which is the bulk of this class, this stuff becomes really important. So one of the ways that molecules like boron trifluoride solve their problems by finding something else that will stick to it that provides the electrons. Ammonia. Anybody ever have that experience where they smell ammonia and it makes you wince? It's kind of a, I don't know, maybe I'm a masochist or something. I sort of like that feeling, you know. It's a potent base. It's not a nice feeling if you get a real hefty dose of it, that's for sure. But a little bit makes you kind of cough, you know. It's a strong base, ammonia, and it's a gas. Boron trifluoride is also a gas. These two things react with each other very exothermically. This compound here. Any formal charges? Okay.
The nitrogen would be -1 or +1, and then the boron.
Nitrogen is +1, boron is -1. Whenever I see nitrogen with 4 bonds around it, I think of ammonium. What's ammonium? Ammonium, right? Whenever I see 4 bonds around nitrogen, I think of ammonium. That has a plus charge. Whenever I see 4 bonds around boron, I think of borohydride. That has a negative charge. Okay. So this compound picked up a negative charge and a positive charge. If you start with 2 neutral molecules and you do a reaction, the products better be neutral. You don't just make charge willy-nilly, right? If you draw a complete chemical reaction and this product is suddenly charged, you better have generated an electron or added one somehow. Okay, neutral, neutral. This is a dative bond. Let's dissociate homolytically. Four electrons around nitrogen is 1 fewer than 5. That thing's got a positive charge. Okay. All right. So what is the valence of nitrogen in this compound? 4. What is the definition of valence? Let me ask this. How many people, let's start, how many people would say 3, the valent, this trivalent nitrogen? How many people think it is tetravalent nitrogen? And how many people think pentavalent nitrogen? What's the definition of valence? 1.
Number of electrons in the valence shell minus number of electrons in lone pairs.
Yeah, that's a definition. Number of electrons in the valence shell minus the number of electrons in lone pairs. How many electrons in nitrogen's valence shell? Oh boy, better know that. 5. Okay. How many lone pairs? 0. Valence is 5. Another definition of valence. How many electrons are used in making bonds? 5. Nitrogen is pentavalent. What's the valence of the boron? 3. Boron only has 3 electrons available to it to make bonds with. So boron cannot be tetravalent or pentavalent. At most, it can be trivalent. So it uses all 3 electrons in making bonds. Okay. All right. Let's do a little more fun example here. Nitrous oxide. How many of you have had laughing gas at the dentist? It's pretty good stuff. All right, N2O combines dative and covalent bonding in complex ways. So I'm just going to draw this guy here. This half the molecule looks right to me. That looks like an oxygen in the ketone. This half looks a little bit funky. This nitrogen's got 4 covalent bonds around it. That looks pretty good. But how many bonds does nitrogen usually make? In ammonia, for example, it makes 3 connections, NH3. So if it's making 4 connections, probably it's providing electrons to somebody else. And it's going to have a positive charge on it. I could dissociate this homolytically and see that there are 4 electrons around nitrogen here. And that would tell you it has a positive charge because nitrogen has 5 in the neutral state. How about this guy? Well, this molecule is neutral, right? So if we have a plus, we probably have a minus. So what's happening with electron pairs out here? 2 lone pairs. And now we've got 8 electrons around that nitrogen. Okay? So this is a nice structure because every atom's got its octet. Okay?
So the molecule that we do before, where we have the separation of charge between 4 atoms, the same atom and the same molecule, that's happening here as well.
Yes.
So is it less relevant for this particular molecular structure?
Well, Mac is pointing out very wisely that we have 2 nitrogens with different charge distributions. And that means this thing is polarized in this sort of a depiction. And in that case, there's no difference between the fluorines and their structure. Here, there's a pretty significant difference between the fluorines. This guy's got an oxygen hanging on, right? Very electronegative atom. So it's not crazy to write stuff like this. But maybe we could sort of rearrange things to make it look better. One thing we could do is push an electron pair over here to that nitrogen. That might move some of that negative charge onto the more positively charged nitrogen and solve its electrostatic issues. But if you're going to do that, let's not violate the octet rule, okay? Let's take an electron pair and push it off of that double bond and onto that terminal oxygen. That can give you a structure that looks like this. Any formal charges? Yeah, when you have a single bond to oxygen, that's one fewer bonds than water, it's kind of like hydroxide or something, right? So probably there's a negative charge here. Split that in half and you'll see you've got 7 electrons around that oxygen, so it's going to have a negative charge. This guy still got 4 bonds. It's like ammonium. So you moved a negative charge onto oxygen instead of onto this nitrogen here. How do you feel about this resonance structure? Is it better than this one? Who likes the one on the right? Me too. That's a good resonance structure. Both of these are pretty good descriptions, actually. Okay. Let's do another one. This time we're going to push the electrons differently. That's the other version of this. Right now we push electrons from right to the left. But when you consider these 3 structures, what you're doing here is asking, where is the charge in this molecule? How is it distributed? This is all the way on the left. That is all the way on the right. Because of the relative electronegativities, you should guess the one on the right is a better depiction. But it's not only that. A little bit of this is probably relevant. This, yeah, it's probably would upset a lot of people if you suggested this was a good description of N2O. Okay. Too much charge separation. You know, in addition to the fact that we got a 2- out here and a plus charge on oxygen, there's a big polarization. Right? It's kind of like that example up there in the upper right. Tons of polarization. All right, it does satisfy the octet rule. Okay, so there is electron pushing and resonance structures, and we're going to do a lot of that. Now we're going to do VSEPR theory. VSEPR theory is a study of geometry. It's not a study of electronic structure. When we do Lewis structures, we basically ignore geometry. There are a few examples where this is not the case. And I'm sorry, there aren't clear-cut rules on this front. Okay, there are some organic molecules where geometry and resonance structure kind of go together. And that's life. So it's not going to be totally clear-cut. But when doing Lewis structures, you can ignore geometry and we won't give you a hard time. Okay? All right. VSEPR is a way to predict shape. And it's great. It really works. But it is also basically, it's sort of like a hokey rule of thumb. Okay? You know, it's like somebody created a system of rules to help you predict shape that has nothing to do with the origins of why they work. Right? Somebody could say from outer space, watch people come in and out of the classroom and say that the students come in here and sing Kumbaya, and that's just like a cultural practice of this society. And that explains why they're there. They take turns, you know, coming to class, 10:10 to 11:25, and so on. And they would be right. They could predict and say, you know what, they're always going to show up here. It's Monday through Friday, 10:10 to 11:25, because they're singing Kumbaya. And of course, we're not. But they would be correct that that's the schedule. All right. VSEPR is like that. It's a system of rules for predicting what happens, even though it is not based on reality. Okay? All right. So it's important that you can predict shape. This kind of makes it possible to draw a reasonable looking substance. People call it an empirical theory. A lot of theories are empirical. They predict properties without knowing the origins of something. I call it physically inaccurate. Okay, but predictive. All right, so Lewis structure. Something like ammonia. No shape implied. A VSEPR structure. Like this. And this bond here is approximately 109.5, right? Because the tetrahedral angle is 109.5. Experimentally, it's 107.3. Okay, so it's less than 109.5. Why is it less than? Well, it's because, so says the empirical theory, electrons are bigger than bonds and they take up more space. And so the hydrogens move away from the electron pair. It's just a mnemonic for remembering. Right? It really has to do with hybridization. For the VSEPR theory, you know the rule is the electrons take up more space, the bonds get out of the way, and that means that this angle here is going to be less than the ideal tetrahedral angle, which is 109.5.
So you said it has to do with hybridization. Is it possible using like quantum mechanics to like calculate and derive that angle, or?
Yes, definitely. Yeah, computer's pretty good at predicting geometry.
So the lone pair, I was reading the book that said that for this particular molecule, the lone pair spreads out over but the orbital itself, the shape of the orbital has to do with the localizability of the particular lone pair. So it can happen if that's an p orbital or an s orbital. Its ability to push bonds away is affected.
Yeah, so the real physics of why it takes on this shape has to do with how the electrons partition into the orbitals of the nitrogen atom. Right? The nitrogen's got an s and 3 p's to give to make bonds. Which orbitals are more advantageous for it to give electrons away in? To answer this question, you need to know about how well electrons penetrate to the nucleus and the ionization energy of the orbital. Hydrogen is pulling electron density off of the nitrogen. Which orbital gives it up more easily, P or S? The P does, because the S penetrates to the nucleus better and it experiences a greater charge, positive charge than the P orbital does. So it's advantageous for the nitrogen energetically to arrange its electrons in S's and P's in a manner that makes that charge transfer less costly. Okay, so it uses P orbitals in bonding and it puts the electron pair in the S orbital preferentially. Is a limiting structures kind of description. Okay, so it's not just all S lone pair, all P bond pair. It's some hybridization that's intermediate. So it's not really sp3. Okay, it's like S.8. Well, I don't know how you do it. How the hell does that work? There's not as much hybridization, basically. Okay. Yeah.
You said S penetrates closer to the nucleus, but S also extends the furthest, right?
Yes.
So why is that not S?
This is a balance we're striking here. Okay, so that is a good principle when analyzing which orbitals are advantageous for bonding. Yeah. More energy? Yes. Yeah, that's exactly the reason. We'll come back to this issue about hybridization in a little while. I want to make sure we get through some more examples because you need this for your problem set and we are out of time. Okay. All right. So let's do another example. Sulfur dichloride. Now, people, when using VSEPR theory, ask what the steric number is. And the issue is, what's the number of things around the sulfur? 2 bonds of sulfur, kind of like hydrogen sulfide. You know the valence, the Lewis representation of water or hydrogen sulfide. You got 2 lone pairs, 2 bond pairs. So the steric number around sulfur is 4. 2 lone pairs and 2 bond pairs. Okay. And what shape is the ideal shape for a steric number of 4? It's a tetrahedron that most evenly distributes the electrons around the atom, says VSEPR. Some things with 4 bonds are flat and planar, square planar. Some things are tetrahedral. So VSEPR what's that angle? Well, it's the tetrahedral angle. Nah, not quite. It's not quite the tetrahedral angle because lone pairs are bigger than bond pairs. So it's going to be a little squished. This is going to be less than 109.5 degrees. And that's how you write it out on your homework set. Tell me the angle relative to the ideal angle for this shape. 4 is a tetrahedron. Tetrahedral angle is 109.5. It's going to be less than that because we have a mixture of lone pairs and bond pairs. Let me do one more example, okay? Yeah, well, I think at this point, unfortunately, we're not gonna, maybe you guys have enough. You'll have to read the book in order to do some of the problems if I don't finish, which I'm not gonna finish. So unfortunately, I think this means that we're gonna have to save the problem set for Monday of the week following. There are a lot of people who've been asking for extensions anyway. So we're going to change that. All right. So it's not going to be due. Wait a minute. When is it due? It's due on Wednesday. So we're going to shift the due date to Monday. Baraket, would you send an email around after this? Yeah. But due date is going to be shifted to Monday so I can finish the material But you're gonna get another one back on Wednesday anyway, the next one, okay? All right, so instead of trying to blast through the material, there are 2 questions. Do we want to do those now, or are you satisfied?
I was just gonna ask, at what point does the like atomic size, push that angle out far enough to actually be close to one another?
You guys, can you hold on putting stuff away again so I can hear? TJ, would you ask that question one more time?
I was gonna ask like atomic size, at what point does it push the bonds out far enough so that it is actually one another?
So, interesting question. So TJ said, you know, heavier atoms are bigger, there's more space, you know? This whole effect of pushing the bonds around, less significant for a bigger atom. This idea of the bonds being pushed around is mostly baloney, okay? So don't use it to try and describe what the molecule is going to do. To predict the shape beyond what the sort of ideal shape would be for a steric member of 4, you need to think about ionization energy of the orbitals involved, and things get tricky. One.
What about if all atoms are very electronegative? If they go for over one?
So we'll do electronegativity and influence on shape when we talk about hybridization next time. Okay, homework set, now due on Monday. But office hour is not moving. So if you want help, tonight's your night. All right, thanks, everybody. Well, we're gonna give you another problem set next week. On Wednesday, it's gonna be due in a week, so we're not gonna delay the subsequent problem sets. Yeah, you'll hand it in on Wednesday, and the next Wednesday, you're gonna get another one. You're gonna turn this one in on Monday, but on Wednesday, you'll get another one. No rest for the weary. Yes. Okay. No, I totally understand here. I appreciate you letting me know ahead of time. Not a problem at all, especially this time. Real time. And thankfully, all of the lectures will be recorded. So. Yeah. Well, have a nice holiday. Yeah, you're welcome. Here, I'm going to just stop this recording.
So exactly.